Hey everyone, so this is our first video all about circles, and there's a lot for us to learn about circles, more than you already know. So this first section is 10.1. Section 10.1, we're going to talk a lot about vocabulary. So there's going to be some words that are super familiar to you guys, and then some words that are completely new. And we are just talking about in this video lines and segments that intersect circles. So we are going to see how lines and segments interact with circles and the different lengths that appear and measurements that appear. So let's get started. First of all, this definition of circle, hopefully it's one that's a little bit familiar. The formal definition of circle is set of all points equidistant from a given point called the center. So we could get a nice visual here. I've got a circle. That center point is really important. Let's say that center point is called A. The formal definition says that all of these points that are on the circle are all equidistant. What's that mean? The same distance from that center point. That's what makes a circle. All of those points on the outside are the same distance, equidistant from the center point. That center point is really important, and the letter that's associated with it, because that's how we name a circle. You can name a circle by its center. For example, the circle right here is named circle. We have that notation, circle A. We use the center point. Okay, so some more vocab. Special segments of a circle. Let's just look at this first one, chord. So really, a chord is just a segment whose endpoints are on the circle. So that's really important. Both endpoints are on the circle. So let's look at this example. I could say PQ is a chord. I can say AB is a chord because both of the endpoints are on the outside of the circle. Let's check out our next definition. Diameter is, notice it's a chord. So it's exactly that same definition. That means the endpoints are on the circle, but this time, more specifically, it goes through the center, okay? And so we've known that about a diameter. We know right here that AB is our diameter, the only one, segment AB, that's in that picture. Notice it was a chord. So a diameter is a chord. Radius should not be new. It's a segment that has only one endpoint on the circle and the other endpoint on the center. So when we name radii, we always use the center point first. So when I name the radii in this circle above, we're going to say OB. Segment OB is a circle, is a radius. The center is O, right? I could say there's a radius at OA and also at OC. Anytime I have a segment that has one endpoint on the center, the other endpoint on the circle. All radii in a given circle are congruent because remember, all points are equidistant from the center. A radius is not a chord. This makes sense because a chord has both endpoints on the circle and a radius just has one. These next two vocab words are brand new to us, so let's check them out. Secant line. So it's a line that intersects a circle at 2 points. So there's a special name for it. Who knew, right? When I have a line that intersects the circle at 2 points, it's called a secant line. So I could say CF, line CF is a secant line, and then I can say DF is a secant line. They intersect the circle at 2 points, okay? So of course, if it intersects 2 points, it's a secant line. What about if it intersects at 1 point? That's when I have a tangent line. So this tangent line is in the plane of the circle that intersects the circle at exactly 1 point. So here I've got line AB. Notice it just kind of touches, just barely skims the edge of the circumference of the circle. So I've got A, and I want to write this over here actually. AB is the line AB is the tangent line to that circle. It's really important that we have a name for where it intersects. It's called the point of tangency. So for example, the point of tangency here is point B. That's where the tangent line, intersects the circle, just at that one point. Just one way of how you could remember this. T for tangent. Notice if you draw like a T, there's only one intersection right there. Secant, I think about like second. And we need 2 points of intersection. So that's just 2 ways to remember the difference between secant and tangent. So let's practice identifying all of these different vocabulary words in a diagram. So let's do A. So the diameter here, remember diameter has endpoints on the circle and it goes through the center. So we're going to say AD, segment AD is the diameter. See that right there. The radii, we start with the center, so that's C, and we go to the circle. So I've got CD is a radii, and I also have CA as a radii. Let's name some chords. So remember, a diameter is a chord, and then we can also say BH is a chord. Endpoints are on the circle. Secant line intersects twice. I've got this line right here, KG. And we can call this a line as well, AE is a secant line. And tangent line intersects just once. GE would be our tangent line. Okay, how about you guys try 1B? Pause this video, and my answers are going to be under that gray blob. And you can check your work. Some things to note, you might have similar answers. Your letters could be flipped. That's totally okay, except for the radii. Make sure that the C is first. There is only one secant line. There is only one tangent line, so your answer should be mine. If you have GA, that's also okay, or ED, that's okay. Chords, that's okay with as well. Diameter, that's okay with as well. Let's keep on moving here. The next two are theorems that I wanted us to chat about. We've got tangent line to a circle theorem. This theorem tells us that when we have a tangent line to a circle, then the line is perpendicular to the radius at the point of tangency. So notice here's my tangent line. Here's my radius. At the point of tangency, that's point P, it forms right angles because we have a perpendicular lines, perpendicular segments. That's this first theorem. That's really important. Anytime you see a tangent line, we've got right angles at the radius, at the point of tangency. The next theorem we have says it's the external tangent. So external means outside. So already we're thinking about outside lines, outside tangent, external tangent congruence theorem. If two tangent lines share a common endpoint outside the circle, so notice I've got tangent line A, right? That's a tangent line, and tangent line B. Here's a tangent line. They intersect right at that pink point. Then these two segments are congruent. That's congruent to this segment. So I can say A equals B. And that'll help us solve diagrams. So let's practice here. Let's check some of these out. We're going to put both of those theorems together to solve some problems here. Okay, so ED is tangent to circle O. As soon as I see that ED is tangent to circle O, I know I have a right angle, and we can draw that in. So then what is the value of X? Well, I see I've got a right triangle. We know the sum of the interior angles of a triangle is 180, right? We've learned that all year long. So I'm going to subtract 90 and 38 from that to get our angle x. And so we get for angle x equals 52 degrees. Let's check out problem 4. EC and ED are tangent to circle A. As soon as I see here's EC, I'm going to mark a right angle. As soon as I see here's ED, I'm going to mark a right angle. If angle A is 120, let's label it. Find the measure of angle E. Here's measure of angle E. What we need to notice here, guys, and I think you're going to be like, oh my gosh, this is crazy. Right here, I've got a quadrilateral. Good thing we just finished learning all about quadrilaterals, right? Quadrilateral, we know the sum of the interior angles of a quadrilateral is 360 degrees, right? So I know the measure of angle E is going to be 360 minus 120 minus 90 minus 90 to get that last angle, and we get 60 degrees. Okay, let's check out another one. So now let's use, we're going to think about the same exact thing. What is the radius of angle A? So I've got a tangent line, right? I've got CB as a tangent line. I know I've got a right angle. Look at the big picture here, guys. What kind of triangle do I have? I've got a right triangle, and there's one formula that we have learned and used for a really long time with right triangles, and that's Pythagorean theorem. It's the only formula that we can use for right triangles, and it's the only formula that you can only use with right triangles. Let's label the sides we have, because notice we're trying to find R. So I can say here's A, here's B, because C has to be the hypotenuse. And then let's substitute in what we know. A is that R squared, that's what we're trying to find, plus B is 16, substitute that in. Notice what C is. C is that entire side. It's not just R and it's not just 8, it's 8 plus R, right? That entire side, these two need to be added together, so we'll square them as well in Pythagorean theorem. And now we will do some simplifying. So I've got R squared is R squared, plus 16 squared is 256. We have to remember 8 plus R quantity squared is 8 plus R times 8 plus R, right? Just like sidebar, 3 squared is 3 times 3. When we have squared, we multiply it by itself. So then we're going to have to do some foiling, some distributing. I'm going to get 64 plus 8R plus 8R plus R squared. And then write that in standard form. I'm going to have R squared plus 16R plus 64. Now we'll combine like terms. The R squareds are going to cancel. I'm going to subtract 64 over. And I'll get 192 equals 16R. Divide by 16. R equals 12. And that's the radius. Okay? We have to remember that when we have right triangles, because of that theorem, we must use Pythagorean theorem. Okay, 2 more to go here. Verify that ML is tangent to circle N at L. So if we want to verify this, we need to prove that we've got a right angle. We're going to use that Pythagorean theorem again and make sure that this Pythagorean theorem equation holds true. So we're going to go 7 squared plus 24 squared. Does that equal 25 squared? If this is a true equation, then I know we've got a right angle. Then I know ML is tangent to circle N. So I've got 49 plus 24 squared is 576. Does that equal 25 squared, which is 625? Add 49 plus 576, we get 625. And I don't need the question mark anymore, because 625 does equal 625. So I can say ML is tangent to circle N. And one last one here, guys. AB and AD are tangent to circle C. Notice they both intersect at A. As soon as I see that they intersect at the same endpoint, I know these segments are congruent. If they're congruent, they're equal to each other. And there's my equation that we're going to solve. X squared equals 9. Square root both sides. I get x equals a positive and a negative 3. Okay, so guys, this is all about circles here. This is the very beginning. If you've got questions, let me know. Great job.